and the death ray. Okay, good. Yes, well, thank you very much to the conveners for inviting me to give this talk today. I thought I'd start with a little bit of geological entertainment. This is Fantasy Canyon in northeastern Utah, and Fantasy Canyon is a real place. It's not a place where modelers like me come from. The particular significance of it is that it is a rock where relatively durable cements have cemented up the fracture system while the sandstone surrounding the fractures is relatively weak. And the result is that one has three-dimensional fracture network. It's eroded out. You can visualize almost like molds. This is not my best picture of the 3D networks, but I thought I would throw in here this particular picture because that black line is a gilsonite dike. And gilsonite being a natural high-pressured fluid that came off an oil reservoir. And it's an example of a geologic, natural occurring geologic frac, which is not interacting too much with these natural fractures here, but that's, again, you can see the gilsonite dike right there, and that's the dike going through there. There are much bigger ones in Utah, they're mine, but this little one here is quite entertaining. So the topic of my talk today, after that brief introduction, is the influence of fracture network geometry on production from unconventional reservoirs, and I'm Tom Doe from Golder Associates, part of the Fragment Technology Group in Redmond, Washington. And I have to thank my, I'm showing material here that my clients prefer not to reveal, so I'm respecting them on that. But the outline is that we're going to look first of all at production behaviors, idealized production behaviors from constant size, constant space hydraulic fractures. I call them fish bones, or another friend of mine calls them discs on a stick. And then we'll go into complex hydraulic fractures, fractures that are controlled by pre-existing but non-conductive natural fractures, and then we'll finally look at some examples of production from a stimulated volume that does contain conductive natural fractures, and that's a Northeast gas shale. Frac design 101. Well, the key to frac design in an ideal situation is two things, is to control the frac spacing and control the well spacing. And ideally, you want to have the frac spacing that's close enough to optimize the recovery, because when you start producing from a fracture like this, you'll get a square root decline in rate if you're producing at constant pressure, a square root decline in rate until the fractures start to interfere. And ideally, you'd like that, and at that point, the rate drops dramatically. So you'd like when that interference starts to occur, that you're at an economical rate. You don't want to hit an uneconomical rate before you've depleted the volume between these two fractures. So that's the key thing that controls fracture spacing. Again, close enough to optimize recovery so that you're still at economical rates when they start to interfere, but far enough apart that you're not wasting time making fracs that are completely unnecessary. The second thing is to figure out what the length of the fracture is, so you can, either by zipper fracs or other things, put your fracture, your wells at appropriate spacing, not leaving gaps for production. So that's frac design 101 in a nutshell. Now, what I'm going to show today are discrete fracture network models of various complexities, and a key to this, as Dr. McLennan showed, is to understand matrix fracture interaction. And we use two ways to do this in our fracture network codes. One is we put matrix slabs. We associate with every fracture surface a matrix slab of some depth. For constant spaced fractures, we can make these slabs exactly half the distance between them. And this is something where we can have relatively large coarse discretization of the fracture, and the matrix slab is a 1D solution associated with the fracture that we can do very finely discretize. It's very numerically efficient. However, it only does a certain constant space slab. It doesn't account for fracture complexities and possible overlaps. So for more complex situations, as long as we're primarily dealing with a layer, then again, our models are pure fracture network models, but we can put what we call a matrix fracture into the whole system that connects all the fractures, and we can give that matrix fracture the storage properties and the permeabilities of the matrix, and thereby represent at some level flow between the fractures and the matrix at some complexity. Now, there are two major classic models of fracture matrix flow. One of them is the bilinear model, well known as Cinco-Lay for those of you who are into well test analysis. And it's a model you use when there's higher matrix permeability. And it has a characteristic quarter slope pressure derivative. The pressure derivative, by the way, I don't have time to go into it in detail, but it's basically the semi-log semi-log derivative of your pressure data. And the semi-log derivative gives you a flat line when you have radial flow. And when you have a fracture that's finite conductivity, then it will create a quarter slope. And that's when you have high permeability matrix. A more recent model that's been developed by a number of people at School of Mines and Texas A&M is what might be called a trilinear flow. In the trilinear flow, you first of all produce from the fracture before you produce much from the matrix. And it's linear. That is, rather than being radial to a point, these are parallel flow lines. Linear flow produces, by the way, a characteristic quarter half slope. It's basically pressure and rate are proportional to square root of time. So in trilinear flow, you basically deplete the fracture before you start to get significant flow from the matrix. Now, the way this, in trilinear flow, you get a series of linear flow steps that are at this half slope, the square root time, and then you get a steepening of the derivative, which is the depletion of that fracture feature. Then you get another linear curve, half slope, which is associated with linear flow from the matrix. Then it depletes, and then eventually you might get a third linear flow, which is the entire footprint. Now, to show that a little more clearly, this would be fracture linear flow here, our first half slope. So this is a square root varying with time, rate or pressure, where you're getting linear flow, again, parallel flow lines. Maybe look at this one here. And then you reach the end of the fracture, and the whole thing starts to deplete before you start to kick in the matrix. Then the matrix kicks in, and we start to see linear flow, again, parallel flow lines from each matrix block to each fracture surface. Again, the key thing here is linear flow from matrix block to fracture surface. That creates a second half slope. And then once the fractures start to interfere, you get another depletion. And then finally, the entire stimulated footprint of this thing can act as a single linear source to give you formation linear flow, which is probably you don't see very often because it's rather long in time. And by that point, the rates are really pretty uneconomical in most things. Now, in our fracture network simulations, we can show that this model actually varies continuously depending on the matrix permeability. So we have, these are equivalent rate derivative curves. So this is what we can deconvolute. Most wells have variable rate and variable pressure, but we can deconvolute these to equivalent constant rate and constant rate variable pressure. So what we see here is a series of simulations for a 200-meter fracture varying from 2 nanodarcies up to 1.25 microdarcies, not really permeable stuff. And what we see here is that we got our half slope down here. The first one is completely impervious matrix. There's our half slope. That hits the end of the fracture, and then we're completely depleting it. And then as we increase the matrix K, notice how that slope gradually decreases, and it moves from the half slope of trilinear flow, a fracture part of trilinear flow, to the quarter slope of bilinear flow. Usually we think of these as two different regimes, but in fact, as you vary the matrix K, there really is a continuum of behaviors. So this is the early time when we're looking primarily at what the fracture is doing and not a lot of matrix coming in except through this bilinear flow field. Then in late time, we have the depletion, which is the boundary flow, and eventually this will go to another half slope, which would be our matrix linear flow, which is right here. And as we make much more conductive matrix, then we go straight from the quarter slope bilinear flow into the matrix depletion, where we start seeing the fractures interfering with one another. So these would be really idealized things for the disks on a stick model. Now, one thing our client was interested in was, could you determine the length of the fracture? And actually you can from this kind of model, But most of these things are happening. This is for an Eagleford type case. There's 50, 100, 150, and up to 400 meter fractures. And you can see the departure here shows is dependent upon that fracture size. But you see most of these things are happening within a period, for relatively tight rock, they're happening within a period of hours to, minutes to hours. And usually the well's not settled down enough at that point to really get much. It's very early time behavior, so I'm not sure it's really very practical, but a lot of the fracture stuff is happening quite early. Now, the next part we'll take a quick look at is fracture network stimulation. We're going to look at that same case where we have a natural fracture network based on the Eagleford for a footprint of this kind here. We generate natural fractures based on orientations from a variety of sources, both surface outcrop mapping, and that's a fracture network. And then we do a simulated stimulation in FracMan, which is a relatively simple approach where we create a fracture network and we simply determine which natural fractures can open given our pumping pressures. We adjust the apertures of the fractures and their lengths based on an elastic solution with a mass balance based on some assumed leakage functions. But basically we're balancing the elastic opening with the aperture growth and length growth. And we will grow on natural fractures if they can be opened. If there are no fractures that can be opened, then we'll just simply grow a new fracture in the sigma h max direction. One key thing we use to calibrate this relatively simple model is to compare microseismics with our observed microseismics with actual microseismics to get two things: the distance of microseismic growth and the complexity. So depending on the fracture network and the stresses, you'll either get very strong microseismics, simulated and actual, or you'll get more diffuse clouds of microseismics. So when we do a network like that, it's quite different from what we had before. So instead of depleting the constant spaced fractures, you see that each stimulation is relatively complex. So this is depleting the fracture, we start to deplete the matrix here, and finally we're fully depleting each stimulated volume. And you notice that within these you have smaller blocks that make much more complex behavior. So instead of having one block size, we now have a whole distribution of block sizes that really changes things quite a bit. So this is some deconvoluted data from the Eagleford. The early time is not that great, but this is our reference half slope, and this would be the unit slope of depletion. So half slope linear flow, unit slope depletion. And what you see we get is something that lies somewhat in between this, as if we're getting some linear flow, we're also getting some depletion going on at the same time. As larger blocks are continuing to deplete linearly, but then we have smaller blocks that are completely depleted that gives us this more complex behavior. So this is actual production data deconvoluted, and there's a distribution of what we get with different realizations, something between a half and one, the linear to the depletion. And then we have, this is our simulations on complex fractures, and again we see the same reference half slope, reference unit slope, and we're getting our stuff in between. So that's one of the ways that fracture complexity is going to alter the production characteristics. So a conclusion from this is that realistic fracture networks involve both hydraulic fractures and stimulated natural fractures, and the variable block sizes of realistic networks obscure the transitions from fracture to matrix flow and give us these derivative slopes between a half and one. So the next thing I'm going to look at in just a couple of slides is another case which is from an eastern gas shale. And this figure here shows the color is topography. This is showing the microseismics and the wells. And you notice this is actually only this small area right here. The rest of this response is seismic response from a method called tomographic fracture imaging, developed by Peter Geiser, among others, and currently developed further by Global Geophysical Inc. El Alcazar is our colleague on this part of it. And this is looking at total seismic energy produced during the fracturing and stimulation process. And you can see the total fracture seismic energy is covering a much, much larger cloud, some of these actually following things that look a bit like the topographic lineaments. Now you might say, well, does this mean anything? Well, in this particular field, a bit more was done than usual. First of all, the fracturing was done with gas rather than with water. And there were tracers put into the gas that were observed in wells up in this area. A farmer who had an illegal, unregistered gas well in this area for his own personal use became very upset when it started to produce nitrogen. So that was down in this area here. So there is some validation that, in fact, the effective stimulation is quite a bit larger than this microseismic footprint. To build a model of this, in this case I was using the simple hydraulic fractures. We built a model of hydraulic fractures, the discs on a stick. Then we also had conductive fractures that were identified in the return gas during drilling, so they could see kicks of gas that were showing conductive natural fractures during drilling. We put those in as deterministic features. Then we put in those tomographic lineaments here, those are the light green ones, and then we fill in the rest of the volume with stochastic lineaments, which we know must be there, but are not actually observed farther away. So that's a full fraction network model. And the entire thing here is, there's the discs on a stick, and you see a much larger footprint of these things going away from the well. As it turns out, most of the production is still coming from this area here, but you've got a much larger zone of influence from the natural fractures. So some conclusions. Well, first of all, bilinear and trilinear flow are continuum of solutions with changing matrix permeability. That's for the case where you have constant spaced, constant length fractures, which I'm not sure we have, but that's one way to view these things. If we have stimulated natural fractures, we will create a range of block sizes that gives you something between the depletion and the linear flow of the trilinear flow model. So we get something in between as we get a spectrum of block sizes. If we have natural conductive fractures, they tend to extend the pressure footprint of the production, although I didn't show the figures here, but the bulk of the production is still coming from that stimulated region around the hydraulic fractures. So I think that's everything in my talk. I think I could get a little bit more on schedule. And I'll point out that much of this has been put out in two papers from the Unconventional Resources Technology Conference from this year and the year before. Al Lacazette's been a big help on this, and you can look them up in One Petro if you like under my name. Or if you send me an email, I'll be happy to send you copies of these that will give you much more information on what I've presented here. So thank you very much for your attention, and I'm open to questions.
Do we have any questions?
Good.
I have a question. What is, comparing the ideal and the less ideal condition, what are the pieces of information that we most critically need to advance the thinking about what we're doing with these fractures?
Well, I think as far as the critical information, I think as we've seen already with Professor McClendon's talk, is I think models that take into account fracture complexity, calibrating these things with production data as I've shown here. And I also think that there would be a lot of value. I know Lawrence Berkeley Laboratory is looking, there was a very good town hall earlier this week on initiatives for better understanding the subsurface for lots of reasons, including this. And I think better controlled experiments in the field, perhaps closer to the surface, where we can mine out some of these things, drill some of these things out, validate some of these models, will be tremendously helpful. One thing I took out of the talk that is also of interest that I hope to publish on sometime in the future is there were some very interesting hydrofracks done at Oak Ridge that, in shales that showed some of these behaviors. So that was a long, long time ago when they were injecting radioactive waste into shale. Anyway, I won't go into that unless you want to talk about it over coffee. So,
thank you.